Hello guys, welcome. Myself is Saswata Kumar Das. So I will be teaching about the uses, the applications of automata theory, game theory. So let's start. So yeah, I will even give some real life examples, which will be easy for you to learn more deep and go more deeper. So today we are going to learn about application of automata theory in game theory. So it's done by me, Saswata Kumar Das. This PPT. This PPT will be available in the end of the video or in the description in the YouTube link. Right. So first we'll see the abstract. What are we going to learn about this? What are you going to learn? According to game theory, giving players tactics directly affects how well they perform, right? In a game theory, we give the tactics to play, it will affect how well they perform, right? One way to give players strategies is by utilizing the power of automata. So here we will use the power of automata to utilize the gave the player strategies. Okay, it was discovered that game theory frequently uses finite automata, adaptive automata, and cellular automata. Finite automata have only found to be useful for simple strategies that are currently being used. Okay, the finite automata is just used. It's found to be useful for the simple strategy. For complex environment or the complex strategy, we'll be using adaptive automata and cellular automata. They're heavily used. They're heavily used in the complex environments where a large number of involved participants like humans, computers, program, etc. are present and complicated strategies are consequently required. Now we will see an introduction. Okay, so what is the introduction? Any issue including active players and their activities can be viewed as a game. Okay, when a motorcycle rider makes a plan to navigate through congested areas, they are essentially engaged in the driving simulation instead of navigating the congested area, right? They'll find the shortcut, like we have Google Map, and this is also a part of game, right? It's in game theory. Users who place bids on websites, the bids are truly participating in an auction. You know what's an auction, right? They place a bid that 15 crore, 16 crore, like bidding apps. We have many bidding apps, right? My 11, Dream 11, you know all these things. Let me take a better example like IPL auction, right? So let's since it's IPL season, so let's take an IPL auction as an example. Yeah, perfect. So yeah, so here you can see, here we have RCB, CSK and Mumbai. Let's take, we have these three teams. RCB wants Dhoni, CSK wants Dhoni, and Mumbai. All 8 teams are bidding for Dhoni, right? And what's the base price of Dhoni? It's 2 crore, and the bidding goes on larger and larger. This is an example of bidding auctions, right? It's a bidding game. It's a game theory. Here the optimal decision is made. The decision is made by the management that we need to bid for this player according to some budget which they have been given, right? Now any issue like choosing the platform for an election is a political gambit. An economic game is played when a factory owner sets the price of goods. An economic game is played over here. In life many things a game, our life is a game, if I to be honest, right? Of course there are very variety of applications for game theory. These are some applications of game theory we have shown you over here, and there are more variety of applications of game theory. Strategic interactions between people can be examined mathematically using a game theory, right? Now next, let's go ahead. Now, so these were some introductions about game theory. Okay, now what is a game theory and what are its applications? So you may be wondering, why is this guy talking about game theory? Is there any applications of the game theory? Yeah, of course. So what is a game theory? A theoretical framework for convincing social situations among the competing players is known as a game theory. Okay, this is simple definition about game theory. Let's know more about game theory. Game theory is optimal decision making in presence of others with different objective. Okay, so what is game theory? Basically game theory is an optical decision making in the presence of others with a different objectives. How can I explain you this, right? Now yeah, so what is a game theory? As we have written here, game theory is an optical decision making, right? It's an optical decision making, we known as a game theory, and we know many things that optical decision making. Right. So here you can see I have written down, it's an optimal, so not optical, sorry, it's an optimal decision making. Which a decision, it's a decision that is made by everyone in that game. Everyone in that game wants Dhoni, like in the CSK management, all want Dhoni. There's no conflict. There's no conflict in CSK management. They want to buy Dhoni at any cost, at any price, right? So that's the game decision making. Similarly, so next, another example is the mathematical theory of conflicts, right? There may be a conflict like five members in CSK want to take Dhoni, three members in CSK don't want to take Dhoni. So there's a conflict in an interactive situation in which several agents make situation. So in this situation, what happens? A conflict is an interactive situation in which several agents make situation, right? There are several members in BCCI boards, or we can say in CSK management, which will make the situation like they want Dhoni or they don't want Dhoni. For example, I have done here an example. Dhoni is for 15 crore. As you can see here, Dhoni is for 15 crore, right? We are taking Dhoni for 15 crore. So I'll just write in it. So let me explain this in a minute. What's a conflict, right? Now the base price of Dhoni was 2 crore. Okay, now take that RCB has in its purse 16 crores left and CSK has in its purse 16 crores left. Now CSK managements, like management heads, like take five people are saying they want to take Dhoni and three people are saying they don't want to take Dhoni. So there is a conflict between both of them, right? Now how to overcome this conflict? We'll take majority. So majority want to take Dhoni, so they will use the all 16 crore in taking Dhoni only, and even RCB will use, right? And finally, if CSK wins the bid, there's another reason. And even now, both of them won Dhoni, so there's again a conflict over here between the both the teams, between RCB and CSK, right? So between RCB and CSK, there's a conflict. Sorry, the if it was not visible. What was I saying that five people want to take Dhoni and three people don't want to take Dhoni in CSK management. So they have in per 16 crores. So they will see majority. The majority five people want to take Dhoni. So they will take Dhoni. They will go with Dhoni. And here is the conflict between that five people and the three people, right? There's a conflict. To overcome this conflict, we'll take the majority one, right? Similarly, even in RCB, even like for taking RCB, so even in RCB and CSK both want to take Dhoni in that team, right? RCB and CSK both want to take Dhoni in that team, sure. So both want to take Dhoni in that team. So how will both take? That's again a conflict. So though the member who will bid the most will take Dhoni. So this is something. It's a simple reason about conflict in game theory, right? This is a game. Bidding is a game. It's a game theory, right? Bidding is a game theory. Correct. Now let's go more deep. Let's go to the next part. So game theory seeks to provide the best possible strategies, decision making among autonomous and rival actors. The real world scenario for events like pricing competition and product introductions, among many others, can be described, and the results can be forecasted using game theory. There are numerous other scenarios, including the detector game, the prisoner's dilemma, which we'll see in the upcoming slides also about prisoner's dilemma. The game theory can be cooperative or non-cooperative, zero or non-zero, sum and stimulation, or sequential, etc. So the example which I showed you now about the RCB and CSK, about the IPL auction, it is a cooperative, right? It's in BCCI, it comes under BCCI, so it's a cooperative game theory. Okay, and it's a non-zero sum game theory, right? And it's also sequential. Then Dhoni, then Virat Kohli, then Rohit Sharma. They will be taking each and every player. Okay, now every agent has his own preference on the set of possible outcomes. Please remember that every agent, like every member of the team CSK will have its own preference on the set of possible outcomes. They may take Dhoni, they may not take Dhoni. Right? Next, we'll see next an example. Let's take an example. Okay, it's going to be a very good example. Right? So what does here it says? So we are taking an example over here. So what does this example say? So let me just note it down and say, right? So what does this say? The prisoner dilemma game is the most popular game. You all know about the game, I hope so. So there are two people that are detained. Okay, there are two people that are detained, the prisoner one and the prisoner two, right? One guy is charged with both of them are charged with the crime and given a court date. Okay, the both of them are charged with the crime and given a court date. Proper? Understood? Yeah. You can see your diagram. You can refer to the diagram. Let me bring this in. Yeah, the prisoner one and prisoner two, right? So there are three cases. Here we are given with three cases: the first case, second case, third case, and fourth case, right? Three cases there are. So what's the first case saying? Each prisoner is approached individually. So I'm going to this prisoner one and I'm going to this prisoner two, and we are approaching them individually by the case prosecutor, who makes an offer. If you confess to your co-defendant, all charges against you will be dismissed, right? So if this guy confesses about this guy, the all charges in the prisoner two will be dismissed, right? But this guy will be sentenced for 20-year jail, right? He would serve for the 20-year jail, the opponent, right? So let me make you understand this by proper diagram. So so let's take, there's a prisoner 1, that is P1, and there's a P2. So what is saying, if P1 confesses, what does the P1 confess? The P1 should confess that P2 has done the crime. P2 has done the crime. Therefore, then we will, the P2 will be sentenced for 20 years jail and P1 will be free. Right? This is the case 1. This is what the case 1 says. I hope you understood. This is what the case 1 says. Okay. Now let's see what the other cases say. Now case 2. What's the case 2 says? If you don't say anything and your partner confesses, like this guy doesn't say anything but the partner confesses, you will be found guilty and sentenced to 20 years in prison, but he will be released. Okay. So what does it says? It says that if P1 confesses, if P1 doesn't confess, so P1 will be the crime and the partner confesses, that is P2 confesses. Okay, if P1 doesn't confess, then P1 will be in the crime matter. And if the P2 confesses, the P2 confess takes the confess, then what will happen? The case will be ulta, right? So P1 will go to the jail for 20 years and P2 will be free, right? This is what the case, it's the same case, case 1, right? It will be a vice versa, right? It will be a vice versa. Next. Now, so next case, case B. If both of you confess, you will still be found guilty, but only sentenced for 5 years in jail. Okay, so if both of them confess that, now the case, what this case says that, this case says that if P1 and P2 both confess, P1 and P2 both confess, right, both confess, then both of them will be in jail for 5 years. This is the case 2. That is the case B according to the diagram, right? Case 2. Yeah, I hope so you understood. Great. Now, what does the another case say? If you both of you don't say anything, both of you say be silent, both will be found guilty and sentenced for guess 1 year in jail. Okay, so if the both of them, like P1 and P2, let's take P1 and P2, right? P1 and P2 don't confess, be silent, then both will be in jail for 1 year. This is the case 3. So, see, according to me, the case 3 is the better option. Like both will be in the jail 1 year. It's a win-win for both. But if one confesses and one goes, then it's 20 years. But the another won't remain silent, right? So that's why this game is known as Prisoner's Dilemma, right? That's why the game is known as Prisoner's Dilemma. Great. Now you can see the diagram over here. Here somewhere, right? 1 minute. Yeah, you can see the diagram. So you can see a diagram. Confess, remain silent. Confess, remain silent. Prisoner A, prisoner B. Great. Now, this is an example of game theory. Let's not know now. Now, there comes the important part, that is automata in game theory. So, basically, what is the use of automata in game theory, right? Participants benefit from game theory applications of automata. So, participants get benefited from the game theory applications of automata. Game theory, however, examines rational decision making in circumstances where there is interdependence. Okay, next, game theory then can only be applied when players play games logically, and it cannot be applied to cooperative games, right? You can't apply game theory in a cooperative game, right? It can only apply in the player which play logically. The following entities often make up the game. What are the following entities? Players, environments, successor function, terminal test, and utility function. So these are the following entities that often make up a game. So let me write down and then I'll show you. Yeah, you should also write down. There's just some important point, that is players, environment, then we have successor function, and then we have utility function, and then we have terminal test. I'll show you this, right? So these are very important. You can note it down. These are the entities. What are these? These are the entities. I'll show you. I have written down. Yeah. So these are the entities. As you can see, player, environment, successor function, utility, and terminal test. These are the entities, right? That are used in game theory. Okay, perfect. Now let's move forward. Player. What does a player do in a game? One team aims to maximize their winnings, that is payoff, while the other team aims to lower their opponent's score. And these participants, though, might be any kind of entity, including people, software, or entities, or other entities, right? Next, environment. Environment is very important, like we saw. So what does the environment do? Which compromises the position of the board. It will compromise the position of the board and the players available moves. Okay. Next, successor function. What does successor function do? The successor function incorporates the actions and provides a list of move or state pairs, where each pair represents a lawful move and the state that results the on that move, right? From that move, sorry, from that move. Terminal test. The terminal test identifies the moment at which the game ends and the terminal condition is attached. Utility function. The value in numbers of for the terminal states is the utility function. The values which are in the number for the terminal states, it is the utility function, right? Next. Now here comes the thing that we are studying. We studied this whole thing about game theory, automata theory, and what is the main topic that we're going to discuss is for today's lecture is application of automata in game theory. Still now you were just learning what is game theory, what is automata theory. So now we will mix up it and we will know what's the application of automata in game theory. Now application of finite automata, right? So what are the applications of finite automata? Going back to 1985, Neyman attempts to capture the reality that players can only perform bounded computations by describing the iterated prisoner's dilemma players as a finite automata, right? A year later, Rubinstein in 1986 makes an attempt to demonstrate how expensive computing may impair an agent's utility. In place of directly selecting a strategy, Rubinstein imagined that players would select a finite automaton to play the game, right? The utility of a player was explicitly stated on a rely automaton's movements and the complexity of the automaton structure, that is the number of states of the automaton. In other words, larger state filled automaton can describe more intricate processes. Halpern in 2008 he said this, as opposed to treating the players as a polynomial bounded Turing machines, as I told. What? So yeah, basically in TOC in this subject we have a finite automata. Okay, in this let's take this as a finite automata, right? Let me do a diagram for that for better performance, right? So in okay, I'll show something else. No, minute. So in this, let's take we are studying in TOC, right? So here we have a finite automata. In finite automata we have DFA, right? Then we have NFA, then we have PDA. Okay, and all the above of these things, we will have another thing called Turing machine, right, which we'll learn later. Turing machine. So this is after a finite automata DFA, NFA, PDA, then comes Turing machine. Okay, what are these? These are all the finite automatas. Turing machine is like a finite automata, like its representation is like a finite automata, but it's not. So why did I take this topic? Like why did I uh, came this topic in my mind? Because here we can see that uh, here we can see that as opposed to treating place as a polynomial bounded Turing machines, okay, bounded by Turing machines. That's why. In game theory, finite automata are now frequently employed. Like it's employed to model player strategies for instances, and the studies carried out by the researchers of the paper cited in B. So these are the studies that is carried out by the paper sided, right? Reveal that the performance of n player prisoner's dilemma has been much enhanced by a finite automata. So that example which you took, right, the prisoner's dilemma, like case 1, case 2, case 3, it is much enhanced by a finite automata, right? Great. Now we will see. Okay. Now in game theory, simple tactics are found to be effectively represented by a finite automata. Nevertheless, since many real world applications don't require complex strategies to attain their objectives, the game theory is interested in describing the basic tactics, right? Finite automata theory. So, what is a finite automata theory? Finite automata are made up of a mixed, sorry, no, I'm not mixed, sorry. It's made up of a fixed finite memory that uses the fixed finite memory to make decisions, and a non-empty alphabet, or we can say transition function, and starting state and the number of final states in transition. So what basically a finite automata has, it has a starting state, it has a non-empty alphabet, it has a transition functions, and it has a number of final states, right? In transitions, the current state of and the current input symbol are mapped into a new state, right? There are two types of transition states, from state A to state B. Let's take two transition states, A state and state B. Input transition will look something like this: A slash R goes to B with a input symbol R, and empty transition is A slash alpha goes to B, which do not modify the input, right? Finite automata are four tuple structures defined by R in terms of mathematics as follows. So this is the diagram. You have new diagram. Even I have drawn it. So let me just show it out. Yeah, here you can see, right? Yeah. So finite automata, right? A input string is R, it goes to B. A input string is alpha, it goes to B, right? Now what is R? R S I F S. You can keep the symbol name as anything. It's not that it's fixed that it should be S I F or S naught. S means the set of states. I is the input of symbol. F is the transition function, and S naught is the initial state. Okay, I hope you understand. We'll see about this also in the upcoming lectures. Great. Okay. Now yeah, so this is what they have done. S is the set of states, I is an input symbol, F is a transition function, and S is an initial state, right? Now, in a game theory, finite automata frequently utilized. For instance, the finite automata can be used to describe the player strategy in iterated n player prisoner's dilemma, INPPD. So n player prisoner's dilemma is what? INPPD. We know what's prisoner's dilemma, right? We just now saw an example of that, right? So it will describe the player's strategy in an iteration way, iteration 1, iteration 2, iteration 3, n times of iteration to explain. The input is observed strategy profile from the other players, and the automaton states represent the player's action. Example, the number of cooperated agents. Therefore, if n represents the number of players in the game, then the set I is defined as I equal to 0 comma 1 dot comma n minus 1. It goes to n, right? Because it's the n iterated n player prisoner's dilemma. The sets of S can be divided into two sets, that is C and D, right? Such that a player cooperate its defect is S belongs to C or S belongs to D respectively. Now the figure below shows an example of a strategy of NPPD with three participants. If we have three participants, like if you have three strings, we have to take four states. Similarly, if you have three participants, there will be a four states. So here we can see the diagram, and I have even drawn the diagram in a proper way over here, right? You can see it. Great. So yeah, now there are four stages in automaton shown in the figure: C1, C2, D1, D2, right? That we have shown now, right? Which the transition are represented by the arcs between the states. The arcs, what are the arcs? The arcs, right? Yeah, they are between the states. Now, as a transition, the transition is above, right? Now, only the numbers connected to the arcs can cause four states to change, which causes a transition. In this illustration, F C1 comma C2 equal to D. F D2 comma D2 goes to C, like etc. like that. Now the starting state S naught, that is starting state is nothing but here the starting state is C1. So we are just defining the things, right, with an empty arrow pointing its direction. The series of plays that follow the demonstrates how the finite automata can be used to define the strategy. So how this finite automata is used to define the strategy, that we will see here now. Yeah. The player starts by choosing C as the starting state. Now the player will choose C as the starting state. Okay, the total number of corporates will be 0 if none of the players from the two players choose the play C in this round, excluding the player itself. Understood? So what this says that the player will choose the C as the starting state. Now the total number of cooperators or cooperators will be 0 if none of the two players choose C in this round. Okay, the current state will move from C1 to C2 at transition 0, right? If none of them choose, it will move to C1 to C2 at transition 0. You can see it's written here 0. Since the current condition is D1, the agent will play D in ensuring the round, right? The agent will play D in the ensuring round. Now, assume that one person cooperates, there will be total of one cooperator, right? So the state changed from D1 to D1 itself. It will be a self loop, right? Here it's a self loop, right? You can see here it's a self loop 0 to 1. So what does it say? So it will be a self loop ensuring that it is next. Assuming that one person cooperates, there will be total of one cooperator. The state from D itself to by 1. The player will once more play D in the following round. Now, so this is some example that I have tried to initiate. Yeah, so I hope so you liked it. Now there are some limitations in the finite automata, right? As we saw, finite automata, game theory, automaton theory, there is also some limitations of this. So what are the limitations? Finite automata has a certain drawbacks as a modeling language. Nevertheless, only regular language can be recognized by finite automata, right? Finite automata can be only regular can be recognized by only regular language. What about context-free languages? What about recursive languages? What about recursive enumerable languages? So there are many languages, right? So I'll just note it down. What are the many languages I shared so that you won't get confused, right? So there are many languages, right? So what are the yeah, so what I was saying that there are many languages, right? Like we have regular languages, which is only the regular languages are only then by finite automata, right? We have context free languages, we have recursive languages, right? And we have recursive enumerable languages, recursive enumerable languages, right? We have these languages, right? Context free languages, PDA, right? Always remember context free languages, and this is used by Turing machines. Recursive languages, right? Recursive enumerable languages are used by Turing machine. So we have these many languages, but what is that? That's the one limitation, that it only supports regular language. It won't support context free language, recursive enumerable language that can't be driven by a finite automata, right? So that's the one drawback of it. In other words, only specified class of input sequences can be guaranteed to arrive to a particular state. Now, okay, right. Now we'll see applications of adaptive automata. Right. What are the applications of the adaptive automata? It has been suggested that adaptive automaton based devices are effective methods for defining complicated languages, right? Complicated languages, we use adaptive automata according to this. I have seen a reference from this. Okay. Adaptive automata include the following crucial characteristics. Okay. An adaptive automaton's efficient accepting process is made possible by the fact that its structures is based on the finite state or structured push down automata. Without the use of auxiliary semantic procedures, adaptive automaton can handle context dependencies in a rigorous syntactical manner. Okay, in comparison to other mechanism, adaptable automata typically have less expensive implementations. It has a less expensive implementations. Alternatives to the current natural language processing systems might be thought of as adaptive automata. As a byproduct of parsing sentences, the structure of adaptive automata can be extended to incorporate transducers, enabling the creation of parse trees. We have seen about parse trees in the upcoming lectures. Now, So here I would like to conclude my video because it's already being too long. So let's conclude here. What is the conclusion? What do you take? What is the outcome of this slide? Like of these slides, one of the elements that substantially affects the player's performance, how the player's strategy are presented in game theory. We have examined the traits and underlying structure of existing automaton types in this work. As a result, we looked into how automata are used in game theory, right? We looked up that. However, our study found that game theory has only sometimes used certain kinds of automata. We discovered that basic agents' behavior have frequently been represented by finite automata and adaptive automata also we saw, right? Adaptive automata, on the other hand, are typically employed to model the behavior of complex agents, right? The quantity of states in an adaptive automaton determines its level of complexity. The ability of those automata to handle the sophisticated tactics increases as we add more states, right? So here we conclude. Okay, so you so before I end this video, let me put a question to you. So as your game theory, right? What we saw? We saw an introduction to game theory. We saw about what is game theory, and we also saw application of automata theory in game theory. So what do you think? Is automata theory really useful? Is it really applied in game theory or not? Right? So is it really applied in game theory or not? You can just come out with a question. Thank you. So thank you. I would end the video here. So thank you for the cooperation. Thank. So this was done by me. So myself, Saswata Kumar. Okay. If you have any doubt regarding, you can just comment it down. Thank you. Let's take a leave. Thank you.